So I'd like to start my presentation. Hello, everyone. My name is Ando, and I'm a PhD student from Western University, Japan. And today I will talk about one of my works during PhD, and which is about the evaluation of business profitability for plant generation of battery-assisted PV, considering bidding to wholesale market. And this is the outline of today's presentation. First, I'd like to talk about the background. Because this work mainly investigates a Japanese wholesale electricity market, and it is an important factor for this work. So first, let me explain about the current situation in Japanese wholesale electricity market. The Japanese government had decided to change the system which is related to electric power system to feed-in premium in 2022, which is next year, in order to encourage the renewable energies, something like the photovoltaic system and wind farm, to participate in electricity market. At present, in 2021, the thermal power plants is the main participants in the wholesale market. And after 2022, it is expected that a large amount of photovoltaic system will participate in the market to boost a carbon-free society. And there are two types of wholesale market in Japan, spot market and intraday market. And the intraday market is considered at this work. So I'd like to explain about the more detail of the intraday market operation process, which is about how to bid in the market and how much income can participants get when they sell electricity through the market. And I will explain this by using the below graph, this one. For example, there is a bidder who owns one PV. First, the bidder conducts the PV power generation forecast in some way, for example, using the machine learning approach, and gets the PV predicted values. And based on these PV predicted values, the bidder finally informs the two information to the market. And one is the offer volume, which is how much we want to sell electricity at the corresponding time. And the other is how much electricity we want to sell. It is about the price. And clearing price will be determined based on the Zaraba method. And next, I'd like to explain how to calculate an income from the market transaction. And this calculation is especially important factor in this work because we conduct a business revenue evaluation using this formula. And briefly, the income from the Japanese wholesale electricity market transaction can be calculated as the following formula. The daily income equals to the set of A plus B minus C and conduct time accumulation. And each set can be obtained by multiplying the amount of electricity they sell to the market and the market price. So what is the definition of the volume A, B, C? I will explain these by using the below graph. And there are three columns. The left one is the scheduled value, which participants submit to the market. And the unit is megawatt hour per 30 minutes. For example, at this time, we assume it is 100 megawatt hour per 30 minutes. And then the middle one is the actual value, which the participants transfer to the grid. And if PV generates 120 megawatt hour per 30 minutes, then 100 equals to the volume A, and 20 equals to volume B, and which we called, this one we call the surplus imbalance. And the right one is the actual value in the case that the PV generates only 80 megawatt hour per 30 minutes. And then the 80 equals to volume A, and a shortage of 20 equals to the volume C, and which we call the sufficient imbalance. And as for the price, the government designs the government designed the price to be that the price B tends to be smaller than price A, and price A is smaller than price C. And from the above formula, we can see that in order to maximize the profit, we need to cope with the imbalance to decrease it to 0 and increase the regular one. And at this work, we use battery to charge and discharge for compensating the imbalance to play this role. And next, I'd like to talk about the purpose of this work. And the purpose of this work is to evaluate the expected business revenue of battery-assisted PV, considering bidding to Japanese wholesale electricity market. And the battery plays 2 roles to enlarge the incomes, which I explained at the next chapter. Next, I'd like to explain the battery control strategy dealt with in this work. There are 2 strategies. One is at the bidding time, which is 60 minutes before the actual delivery time. Battery participates in bidding process, utilizing the volatility of the market price. And at the actual delivery time, the battery charges and discharges to decrease the surplus and sufficient imbalance, which are caused by the influence of PV forecast error. And next, I use this graph to explain more detail. And this, as for the battery participation in bidding process, what battery do is to charge when the market price is low and discharge when the market price is high. For achieving this behavior, a battery optimal bidding is obtained by solving the optimization problem. And the formula is described at my conference paper because of the time limits. And as for the imbalance compensation, the battery charges when the calculated imbalance is surplus and discharge what that is sufficient to decrease the imbalance and increase the incomes based on the rule-based control strategy. And next, I'd like to talk about the conducted numerical simulation. First, let me explain about the condition of numerical simulation. And the market type is the Japanese intraday wholesale market. And as for equipment, there are PV and battery. The PV rated output is 1000 kilowatt, and the location is Tokyo, Japan. And PV power generation data is converted from solar irradiance data measured by a planometer. And as for battery, the battery rated output is changed from 0 to 1000 kilowatt with 100 kilowatt increments. And also rated out capacity is changed from 0 to 1000 kilowatt hour with 100 kilowatt increment. And SOC range is from 20 to 80%. And initial SOC is 50%. And charge and discharge efficiency is 90%. And the evaluation period is 1 year. And time increments is 1 minute. As for the forecast, the market price forecast is conducted by persistence model. And the PV generation forecast is conducted by long short-term memory model. And the evaluation index is the business revenue of annual income, which I explained at previous slide. And in this work, we conducted these 5 study cases in order to know which battery control strategy can maximize the incomes. First, the case 1 is that the only PV participates in the market. And case 2 is that the only battery participates in the market. And the battery also participates in the bidding process. And case 3 is that both PV and battery participates in the market, and the battery also participates in the bidding process. And case 4 is that both PV and battery is considered, and the battery compensates the imbalance. And case 5 is that both PV and battery is considered, and the battery conducts both strategy. And this is the result of case 2, in case that the battery participates in the bidding process. From this graph, we can see that the battery charges when the market price is low and discharges when the market price is high in order to enlarge the incomes. And this is the result of case 4, in case that the battery compensates the imbalance. From this graph, we can see that the battery charges when the calculated imbalance is surplus and discharge when that is sufficient to enlarge the incomes. And although there occur some sufficient imbalance. And this is the result of case 5, in the case that the battery conducts two strategies. From this graph, we can find an important result. When the battery conducts both strategies, it could increase the imbalance and decrease the incomes due to the influence of PV forecast error. At last, the expected business annual revenue result is described as follows. The following result is that the additional annual revenue by adding a 1 kilowatt hour battery to a 1000 kilowatt PV. As we can see from this table, we found that the battery control strategy, which don't participate in the bidding process and maximally devoted only to imbalance compensation, which is case 4, is most cost-effective way. And the revenue is $17 per year. And lastly, I'd like to summarize this work. In this work, the business revenue of battery-assisted PV considering bidding to Japanese wholesale electricity market was evaluated. According to the numerical simulation results, we confirmed that among 4 different battery control strategies, a strategy which do not participate in the bidding process and maximally devoted only to imbalance compensation was found to be most cost-effective. And also, our proposed study framework is applicable to evaluate various cases considering the volatility of market and imbalance price and degree of misprediction of PV power generation. And this is all of my presentation. And thank you for your listening. If you have any question, I will be happy to answer.